Welcome back. In the previous video, we were looking at an investment application of a linear programming where we found these 5 constraints. We found these 5 constraints and we defined this optimization equation. This is ultimately what we want to maximize. So now that we have all 5 constraints written in slope-intercept form, let's go ahead and put these on a graph and see what it looks like. So we have our y-axis here, our x-axis here. This goes in the positive y direction, positive x direction over here, and we're only defining this in quadrant 1, and we'll actually show you why that is in a second. It should make sense because we can't invest a negative amount of money nor get a negative amount of returns, but we'll formally define that in a second with one of our constraints, or 2 of our constraints. We're going to define these each point in 10,000s. That's going to make life much easier on us. This is going to be in 10,000s. 10,000s. Okay. So let's go ahead and graph this thing. So we have our first constraint. Let's go ahead and deal with these 2 constraints first, because these are kind of important. So we have the first constraint is x is greater than or equal to 0. What this means is we're going to have a vertical line at x equals 0. Or we're going to have a line superimposed on the y-axis. Now this makes sense because x can't be negative. X is one of the amounts that we're investing, so we're not going to have anything to the left of this, no negative values. So this is x equals, we're going to find this as x is greater than or equal to 0. And next we're going to have a similar situation when we're dealing with y is greater than or equal to 0. This one right here. Y is greater than or equal to 0 is going to be superimposed on the x-axis. It's going to be for all the values where y is equal to 0, which continues infinitely in both directions. This is y is greater than or equal to 0, and we're only interested in the regions to the right of this maroon line and above this orange or yellow line, or whatever it is. So only in quadrant 1 are we actually going to have our feasibility region, which actually we'll find in a second. So let's take a look at the next one. Let's go ahead and use this one. So we have y, let's go ahead and rewrite this as y is less than or equal to 1 over 4x, which I like using this because it clearly defines what our slope is. So when x is equal to 0, y is equal to 0. So this line is going to start right here, and it has a slope of 1 over 4. So we're going to go up 1 and over 4. And this is our line for y is less than or equal to 1/4 x. It's going to continue infinitely in that direction, and in that direction only. Y is less than or equal to 1/4 x. And I apologize, that's a 4 right here. Okay, let's go ahead and move on to the next one. We have y is greater than or equal to 80,000 minus x. Well, when x is equal to 0, y is equal to 80,000. Well, since these are in 10,000s, we can just move up 8 steps. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to start right here. It has a slope of minus 1, so it's going to drop down 1 and go over 1. And it's going to have a line looking like this. Going through this point, it's going to stop at the x-axis because it's not going to go below y is greater than or equal to 0, so it's not going to go below x. So this is our line, y is greater than or equal to 80,000. 80,000 minus x. Okay, we got one more to do, and that's this 5th one. Y is less than or equal to 100,000 minus x. So when x is equal to 0, y is equal to 100,000 right here. And it also has the same slope as the blue line. They're going to be parallel because they both have a slope of minus 1. So it's going to slope down just like this, and it's going to stop when it gets to the x-axis. All right, and this is defined by the inequality y is greater than or equal to, or oh, excuse me, it's wrong one. It's going to be y is less than or equal to 100,000 minus x. Okay, so these are our 5 constraints. We have them on the graph, so let's go ahead and find our feasibility region by narrowing down the region with each constraint. So let's start We know that we have this red line and this orange line, so it's going to be somewhere in this quadrant. So we have these two taken care of. So let's go ahead and move to the green one. Y is the values are going to be less than or equal to the green line, so it's going to be underneath this green line. We're going to shade. We're going to shade above the blue line because all the values are greater than. So we're going to shade to the right. So this region is how we narrow it down. It's just a process of elimination. And the purple line, we're going to shade under it. So we're actually going to have this as our feasibility region. This looking like a quadrilateral. This is called our feasibility region. Feasibility region. We introduced this term back when we first introduced linear programming. Feasibility region. And this represents all the values, all the points that can satisfy this optimization equation. But we don't want to just satisfy this optimization equation. We want to maximize it. We want to know for what values of x and what values of y will z have its greatest value. And the cool thing about this is, what somebody really smart proved, that we don't have to guess and just pick at random points in this feasibility region and plug them in and see which one's the greatest. That would actually take us forever because there's an infinite amount of points. But we know that one of these 4 points right here on the corners of the feasibility region is going to be the maximization of this equation. One's going to be the minimization, but we're not worried about that. So we're going to try all 4 of these points into the optimization equation, and we're going to see which one's the greatest. So that's how we're going to maximize this thing. All right, so let's go ahead and take one at a time. The first one, this intersecting point, we're going to have 4 systems of equations because we have 4 intersections. And the intersection is when the 2 lines intersect, or when the equations of the 2 lines are equal to each other. So let's take this first one, where the purple line and the green line intersect. So we have system 1 is going to look like this. We have the purple equation right here, which is 100,000 minus x, and we want the values where this purple equation is going to be equal to this green equation. So we're going to set them equal. So we have 1/4 x, and we're going to solve for x. So let's go ahead and add x to both sides. Let's add 4/4x over here so we can combine these fractions in the next step. These 2 terms will cancel. Let's go ahead and flip this so the x is on the right. So we have 5/4x equals 100,000. Let's go ahead and multiply by the reciprocal so we can isolate our variable. These 2 terms will cancel, which gives us x equals 4/5 times 100,000 will give us 400,000 over 5, which is just 80,000. Okay, so we have a value for x. Now we can actually take this x value and plug it in to either of the equations, this equation or this equation. We can go ahead and use this one because if we do so, we'll have y equals 100,000 minus 80,000. We won't even have to deal with any fractions. So we have y equals 20,000. Okay, so this intersection is at the point, let's just go ahead and write it. Let's go ahead and get another color and write them over. Well, let's write them up here. Okay. So we have the first solution. X is 80,000 and y is 20,000. Let's go ahead and not use commas so it doesn't get confusing. So we have 80,000 and 20,000. So this is our first. This is our first solution for these linear inequality equations. So linear inequalities. Using our constraints, we found that this intersection is at the point 80,000, 20,000. So this is x and this is y. So let's go ahead and erase this. Give us some room to make the next system of equations. We're simply going to do 4 systems of equations, 1 for each intersection. And we'll do the next one. Let's go ahead and use this point. So we have the blue line and the green line. The blue line represents the equation, or is represented by the equation 80,000 minus x, and the green line is represented by this equation 1/4 x. All right, so let's go ahead and solve for x here. So we're going to add x to both sides, add 4/4x over here. These two terms cancel. If we flip this, we're going to have 5/4 times x equals 80,000. Let's go ahead and multiply by the reciprocal, which is 4/5. So these two terms will cancel, which gives us x equals 4/5 times 80,000. 4 times 80,000 will give us 320,000 over 5, which will give us 64,000. Okay, we just skipped this, did some math in our head just to save a little space. So we have a value for x. Now we can go ahead and plug it into either one of these equations. Again, we can use the blue equation because that seems very simple. Let's go ahead and use the blue equation, which is y equals 80,000 minus x, which is 64,000. And, well, too many zeros. Okay, and that's going to give us 36,000. So our second solution for our feasibility region for our constraints is the point 64,000 and 36,000. All right, so we're out of time, so we'll actually finish this up in the next video. We'll check 2 more systems of equations, and then we'll plug them into the optimization equation and see which one maximizes this linear programming. So I'll see you in the next video.